Welcome to Sri Sathya Loka Seva Gurukulam online classes. So we've been studying limits and continuity. So we've seen what are limits, how to evaluate the limits for different type of functions, and then what's continuity, and we've been dealing with different types of functions and checking whether they are continuous or how to remove discontinuity and things like that. So let's move on. In this class, we are going to learn about a very, very important special function that's called as the greatest integer function. So as the name suggests, the greatest integer function takes up the value of the greatest possible integer that the variable takes in that particular interval. Okay, to explain better, let us consider this function f of x is equal to greatest integer function of x. So this is how we denote. We denote the mod function by two vertical lines, and two bar brackets are used to denote the greatest integer function. It is where greatest integer function of x denotes the greatest integer less than or equal to that particular value of x. Okay. So now let's analyze this function. We are supposed to find whether f of x is continuous at x is equal to half. So when we need to check whether limit x tending to half f of x that is equal to the greatest integer function. In short, limit x tending to half, we have to analyze whether this function is continuous and analyze at 1 also whether the function is continuous or not. Let's see how we are going to do that. Okay. Now, let's take some arbitrary values. Okay. So, now let's suppose we have to find the greatest integer value of 1.3. Now, what is the integer, the whole number integer that is less than this? Because if you take 2, it is greater than this value. Definitely this function cannot take the value of 2, but it can take the value of 1. You just have to round it off to the nearest integer value. That is the integer value that is less than this particular value that you have, decimal value that you have. Now 1.99, do not round it off to 2, but the integer value that is less than 1.99 will be the value of this function. Now the greatest integer value of 2, since it is already an integer, the value that is equal to it will be the answer, the value that it will take. Now 0.2. So what is the closest integer? That is the integer that is either less than or equal to this, that is 0. And minus 0.2. Now let's observe this on the number line. With negative numbers, you need to be very, very careful. The integer that is less than that has to be taken usually. Now if you take minus 0.2, so the integer that is less than that particular value you need to consider. So what is the integer that is less than that? Always take the integer that is on the left hand side of it on the number line. If you say this 1.3, 1 is here, 2 is here, 1.3 is here. So on the left, the first integer value will be taken. So similarly for minus 0.2, on the left it is only minus 1. So this answer will be minus 1. And minus 3.1, what is the integer that is first on the left of minus 3.1? That is equal to minus 4. So this is how we try to find the value of it. Okay. Now in general, if x falls between minus 3 and minus 2, wherein minus 3 included, that is, you can write it as closed interval of minus 3 comma minus 2 open interval, because we are not including minus 2. Then the greatest integer value of x would be the lower interval, that is minus 3. because minus 2 does not belong to it. It is on the open interval. There is no equal to sign here. Now, next, x lies between minus 2 and minus 1, where minus 2 is included. So, what is the greatest full integer value that x takes? So, let's see on the number line. Look at this. Your minus 2 is here, minus 1 is here, 0 is here. So, your x is between minus 2 included, minus 1 is not included, and in between this. So, if you see, nowhere integer value lies. These are all rational numbers in between. So, the integer value possible that x can take is minus 2. So, that is your greatest integer value that x can take. Let's move on. Between this interval, so let's have a look again. Put the number line. This is 0, this is minus 1, this is 1. So, minus 1 is included. So, this is 0, not included. In between, everything is included. So, what is the integer value that it can take? Greatest integer value is minus 1. And in this interval, of course, it is 0. And in this interval, of course, it is 1, and so on. So, now let's understand this function by graphing it. So, when you graph this function, every interval there is going to be a jump. So, from 0 to 1 when you graph it, from here onwards you have all these values and there will be a open interval here. Similarly, it keeps jumping like that between every interval. So, you can see that it is like a step when you graph it with equal spaces in between the step, and the width of the step is also equal. So, this function is otherwise called as a step function. So, it is discontinuous, but between every interval, meaning interval of two integers, there is going to be continuity. So, in and around a proper fraction, there is a continuity, but the function as such completely is not, in the real number system, is not continuous. So, now let's see if the function at x is equal to half. When x tending to half, the greatest integer value of x, is it continuous? So, how do we see? We check whether the limits exist, and if they take us to the same limiting value, and if the function value at that particular half value here is also same. Let's see. So, let's see what happens when x tends to minus half. What is the f of x value? So, now x tends to minus half. How do we see this? Limit h tending to 0, f of minus half minus this is. So, this is half minus h. So, this is the integer function of half minus h. So, what is the greatest integer value that this function can take? Obviously, you can see that half, the one that is left to half, okay, left hand side of half, my half is here. So, the greatest integer value that it can take is definitely 0 only. So, my answer will be 0 here. Now, when I approach x from half plus, what is my f of x value? So, limit h tending to 0, f of half plus h, where my h is very, very negligible. Again, this is going to be half plus h, wherein half is very negligible. So, absolutely my integer value, highest integer value, the greatest integer value that this function can take is only 0 and not 1, because my h is almost tending to 0. So, again, both are equal. The left hand limit and the right hand limit take you to the same point 0, and I am going to see if x tending to half, f of x is equal to f of half. So, how do I find f of half? So, I substitute half in place of x and see what is the greatest integer value. Again, the greatest integer value is going to be 0 only. So the limits, the limiting value of the function and the function value both are equal. So hence we can decide that the function is continuous at half. So definitely the function is continuous at half. Always remember, when x value, the limit value is a proper fraction, it will be continuous, because every interval between two integers, there is continuity that we can see, two consecutive integers. Now we are going to look into the next part of the question, wherein we have to check if the function is continuous at 1. So we are going to observe the function before 1 and after 1, both from left and right, and see whether we are going to get the same answer value. So now limit x tending to 1 minus f of x is equal to limit h tending to 0 f of 0 minus h, f of 1 minus h, sorry. So here it's going to be f of 1 minus h. So here it is very, very clear that 1 minus h is going to be less than 1. So this, the greatest integer value of this function is going to be 0. But whereas when we see the right hand limit, x tending to 1 plus f of x is going to be limit h tending to 0 f of 1 plus h. So when I take the greatest value function of 1 plus h, it's definitely going to be greater than 1. So the greatest integer value that it can take is going to be 1. So I can see that the left hand limit takes me to some other value, while the right hand limit takes me to some other value. So I can very well see from here itself that there is no continuity in the function at x is equal to 1. See here, at x is equal to 1, there is a break. I can't continue, but I have to lift my pen and draw another line here. So at no integer point, no integer value, this function will be continuous. So this function, as I said, is also called as a step function, because it is very clear from the graph itself that it looks like steps drawn. So now let's move on. Now we have to check whether the function f of x is equal to the greatest integer value of x is continuous at x is equal to 2 by 3. So as I told you, I can see very well that it is a proper fraction. So when it is a proper fraction, it's going to be continuous. But let's see, let's prove it. How are we going to prove it? So we are going to see the left hand limit first. So limit x tending to 2 by 3 minus f of x. That is equal to limit h tending to 0 f of 2 by 3 minus h. So that is the greatest integer value of 2 by 3 minus h. So the number is going to be less than 2 by 3. So what is 2 by 3? Basically, it is between 0 and 1. So the greatest possible integer value that it can take is only 0. Similarly, limit x tending to 2 by 3 plus f of x is also going to be limit h tending to 0 f of 2 by 3 plus h, that is 2 by 3 plus h, the greatest integer value function of 2 by 3 plus h, where h is very, very negligible. Again, the greatest integer value that it can take is going to be equal to 0, because when we apply the limit of h is equal to 0, you're going to get the greatest integer value of 2 by 3, that is going to be 0 again. Since the left hand limit is equal to the right hand limit, we can definitely conclude that the function, the limit exists. So let's now observe the function value at 2 by 3. So f of 2 by 3 is going to be the greatest integer value of 2 by 3. So that is again 0. So since the left hand limit is equal to the right hand limit is equal to the function value, so we can very well say that the function is continuous at 2 by 3. So now let's move on to the next function and we can observe whether this function is going to be continuous or not. Now, at what points is the function continuous in each of the following cases? So, there is a function that is given. We need to say where all it is continuous. So, it means that it is discontinuous somewhere. Let's first study the function and see. Now, this f of x is equal to x minus 5 by x plus 2 into x minus 3. This function, we have to check, we have to read this function in the entire real number system and see whether whatever real number value you are giving for x, will you get a real number as value for f of x. If you see all the rational functions, the functions as fractions with polynomials on the numerator and on the denominator, always will not be continuous in the entire real number system, because at certain points the denominator, if it takes up the value of 0, this function is not defined at that particular point. If you observe this denominator, it is x plus 2 into x minus 3. So let me see the zeros of this particular polynomial. So x plus 2 equal to 0, x is minus 2 and x is plus 3. These two are zeros of this polynomial, wherein at this particular point, both minus 2 and 3, this particular polynomial takes up the value 0. So at exactly x is equal to minus 2, this f of x becomes undefined, because when the denominator is 0, it is not defined. Similarly, at x is equal to 3 also, this particular polynomial is not defined. So therefore, f of x is continuous everywhere in the real number system except at x is equal to minus 2 and x is equal to 3. Now the next function is this. So now we have quadratic polynomial both on the numerator and the denominator. Let's first factorize them and see what happens to the function and then check whether it's going to be continuous or not. So now f of x is equal to, this is a quadratic equation. Now, will I be able to factorize it? So let's first check whether it will have real roots. So b square minus 4ac is the determinant. So we'll see 4 minus 4 into a into c. So the quadratic equation on the numerator, the quadratic polynomial on the numerator cannot be factorized. So we will leave it as such. And because it does not have any real roots, the next quadratic polynomial that we have on the denominator, let's study that. So that is your d will be equal to b square minus 4ac. That determines whether the roots are going to be real or imaginary. So when I find that out, it's 64 minus 4 into 16. Of course, yes, it is equal to 0. It has real roots. It's a perfect square. Let's see how to factorize that. So we have x square plus 2x plus 5 and let's split the middle term. So we need to split it such that when you sum those two numbers, it should be minus 8. And when you find the product of those two numbers, it should be 16. So the numbers are 4 and 4. Minus 4 and minus 4. So x square minus 4x plus 16. So when I factorize this, I can take x common outside, x minus 4 into x minus 4. So this is basically x minus 4 the whole square. So again, this is a rational function. So this will be defined everywhere on the real number system except for x is equal to 4, wherein the denominator becomes 0 and the function is not defined at that place. It leads to infinity. So therefore, the function is not continuous at x is equal to 4. It is continuous everywhere on the real number system except for x is equal to 4. So this is how you deal with rational functions. So today we've seen continuity of different types of functions, the rational functions. And not only that, we learned a new type of function today, that's the greatest integer function. And we understood the graph of it, how it looks. We also saw that it is otherwise called as the step function. And then we tried to read the continuity of that particular function in rational values and also in integer values. With that, we close the class for the day. Thank you. Saira.